Here we're going to talk about periodic trends. This includes atomic radius, ionization energy, electron affinity, and metallic character. The explanation for the periodic trends that we're going to talk about mostly revolve around the effective nuclear charge, which we had just learned about. So starting with atomic radius, there's a few ways that we can measure atomic radius, defined in two different ways. One is a metallic radius, half the distance between two nuclei in two adjacent identical metal atoms. So in just a metallic solid, we can measure nucleus to nucleus, divide that by 2, and that would be what we call the metallic radius, and that would be an atomic radius of a metal atom. Another one is when these atoms undergo covalent bonding. You can get a covalent radius, which is half the distance between adjacent identical nuclei in a molecule. So for example, Cl2, where you have a chlorine-chlorine bond, you could measure the distance between the two chlorines, divide that by 2, and you would get the atomic radius of chlorine. The atomic radius decreases as we move from left to right across a period, and it increases from top to bottom as we move down within a group. This is the atomic radius, not of atoms that are ions. So this is atomic radius dealing with atoms that are neutrally charged, not ions. We'll talk about that in a bit. So here, like I said, the atomic radius decreases as we move from left to right across the period, and it increases from top to bottom as we move down within a group. The moving down makes some sense. We're going to higher and higher principal quantum numbers, so we have a larger and larger shell that we're referring to. Those electrons keep occupying spaces that are farther and farther out, so our atoms are getting larger and larger. Here's a chart of the atomic radii. Those numbers underneath are in picometers, which is 10 to the negative 12th meters, so even smaller than nanometers. So you can see we're increasing the atomic radius as we go down, and that trend holds true pretty well throughout the entire table. But why as we're going from left to right, we're actually decreasing our atomic radius. That maybe isn't quite as clear why that would be occurring. Like I had alluded to, a lot of this is based on the effective nuclear charge. So since, as we're going from left to right, we are increasing the effective nuclear charge, we're adding both a proton and an electron. So your first thought would be you're probably adding a proton and an electron. You would think that things would be getting a little larger, but in fact they get a little smaller because there's more charge in the nucleus and more charge from those valence electrons that will hold those electrons closer to the nucleus. So that's a more powerful attraction, making that whole thing smaller. So we will have a smaller atomic radius moving from left to right, and that is because of the increase in the effective nuclear charge. So the vertical trend for atomic radius is based on the principal quantum number increasing, where the left to right trend is based on Z effective, the effective nuclear charge. Okay, referring only to the periodic table, arrange the elements P, S, and O, phosphorus, sulfur, and oxygen in order of increasing atomic radius. So we'll use that trend, the left to right and top to bottom trend, to compare the atomic radii of 2 of the 3 elements at a time. Sulfur is to the right of phosphorus on the 3rd row, so sulfur should be smaller than phosphorus. Oxygen is above sulfur, so oxygen should be smaller than sulfur. Here we can see that. So oxygen is the smallest. It has the lowest principal quantum number. So it should be a little smaller and a pretty high Z effective since it's farther across to the right on the periodic table. So oxygen will be the smallest. Then sulfur will be bigger, higher principal quantum number. But it will be smaller than phosphorus because sulfur will have a higher Z effective than phosphorus. Another trend that we can talk about in the periodic table is the ionization energy. sometimes just referred to as IE. It is the minimum energy required to remove an electron from an atom in the gas phase. So here would be an example for sodium. Sodium, let's say it's in the gas phase. It's the energy required, so the delta H of this reaction, to form Na plus gas plus that electron. So that has an ionization energy of 495.8 kilojoules per mole. So in order to strip that electron off, that's how much energy would be required. It's not just ionization energy. We have a couple different types of ionization energy. This is the first ionization energy for sodium. It's removal of the first electron. You can have an ionization energy 2, and that would be the energy that it takes to remove the second electron. So you'd be starting with Na plus as a gas, going to Na2 plus an extra electron. That would be the second ionization energy, and so on and so forth. You can continually go out from there. The first ionization energy is starting with the sodium gas that's neutrally charged. The second ionization energy is sodium plus, which already has one electron stripped from it. So this is the definition of ionization energy. Here you can see there's a trend associated with the ionization energy. These are all of the values in kilojoules per mole. And as we move up and to the right, we are increasing ionization energy. Here's another way to show this. So you can see the trend moving from left to right. Let's take a look at maybe the first row, lithium to neon. Lithium to neon is going across. So lithium moving up through neon, you're going across, and you can see there's a general upward trend. We're increasing the ionization energy, and then we're starting back over with sodium on the next row, for example. And generally, as we're going down the periodic table, we see a general decrease. So in general, that's what we talked about. The effective nuclear charge increases, ionization energy also increases. So this is because of the effective nuclear charge, once again. And this makes some sense. That electron is being held more tightly as you increase the effective nuclear charge. So it's going to be harder or more energetic for you to ionize that, for you to take that electron off of the atom. So we see that ionization energy 1 is increasing from left to right across a period. But despite this trend, you can see there's a few discrepancies. I've circled 2 of them here. That it doesn't work exactly correctly. We will talk about why that is the case. So for example, this is one of them. You have group 3A elements. They're smaller than that for the corresponding 2A element. And we actually have some justification for that, some reasoning that we've already learned that we can look to figure out why that might be. We also have another spot that between 6A and 5A that there are some interruptrons. You can see right there that there's a little bit of a trend, and it seems to hold true throughout, whether you're talking about first row or second row. We can actually, like I said, we can take a look at why this is occurring based on those electron configurations. So let's take a look at that first example. We have a group 2A versus a group 3A. These are the ground state electron configurations for group 2A and group 3A. And group 2A, if you are going to undergo ionization, you are removing an electron from the s orbital. And that electron is a little bit harder to remove. As opposed to the group 3A, it's fairly easy to remove that outermost p electron, since its outermost valence electron is a p electron. So that's just a little bit easier to remove. It's at a higher energy level, just a little bit, than the s orbital. So it's easier to remove, and that's why you see that little zigzag occurring. So that's the difference between 2A and 3A. Between 5A and 6A has a similar rationale. Here, it's harder to remove that p electron in group 5A. because it's currently not paired, where group 6A has a paired electron and it is a little bit easier to remove. There is a little bit of energy required to pair electrons, and you can kind of think of this as there is electrostatic repulsion between electrons. So generally, electrons pair all the time, but it does require just a little bit extra energy for them to do that. So it's easier to remove an electron that's already paired, and that's why you see that sort of zigzagging pattern again between group 5 and group 6. So these general trends hold pretty true, but even when we're seeing some discrepancies, those discrepancies we do have some rationale for dealing with. We also have ionization energies that can help us identify what group it is we're referring to. So lithium has an ionization energy 1 of 520 kilojoules per mole. And then there's this huge jump to ionization energy 2. This maybe should make some sense. Lithium, we know, prefers to be a +1 cation. So that first ionization energy is pretty low. It happens fairly readily. So lithium can form a +1 cation quite easily. We've never seen lithium as a +2 cation, and that's can be shown here. You have a huge jump to an ionization energy 2. We haven't talked about why that necessarily is, which we will get to later, but the very basics is that these atoms generally prefer a noble gas core or noble gas electron configuration. And if lithium were to lose just one electron, its outer s electron in a higher energy level, a higher principal quantum number, it will have then a noble gas configuration. If you were to try and take another electron from it, that's now from a lower principal quantum number energy level. And that is very, very unfavorable. So it has an extremely high ionization energy too. Other elements, that's not the case. For example, beryllium, it has a relatively low ionization energy 1 and ionization energy 2. Ionization energy 2 will always be higher than ionization energy 1, and that's because you're trying to pull an electron, which is negatively charged, from something that's already has a +1 charge on it. So that's always going to be a little bit more challenging than taking an electron from something that's neutrally charged, which is what we're doing in ionization energy 1. Okay, so we're always going to see that increase. But for beryllium, it has 2 s valence electrons. Sorry, it has 2 s electrons that are those valence electrons. So both of those can be ionized. You can take both of those off before reaching that noble gas electron configuration. And then you see a huge increase to ionization energy 3. So actually, based on the ionization energies, you can determine which group a particular element is from based on this kind of stair-stepped ionization energies. So I could ask, I mean, where would you expect this big jump to be for something like aluminum? You would go and look at aluminum. Aluminum has 3 valence electrons, so you'd expect it to look very similar to boron there. And after its third step, you would see a very dramatic increase in ionization energy. All right, so let's take a look at one of these. Would you expect sodium or magnesium to have a greater first ionization energy? And then secondly, which would have a greater second ionization energy? So we'll consider the effective nuclear charge and the electron configuration to compare the ionization energies. Remember, the effective nuclear charge increases from left to right in a period, which is thus increasing the ionization energy, meaning it's more difficult to remove a paired core electron than an unpaired core electron. That is another aspect to this. Sodium is group 1, magnesium is beside it in group 2. Sodium has 1 valence electron, magnesium has 2 valence electrons. So because of this, you'd expect the ionization energy for magnesium to be larger than the first ionization energy for sodium. Magnesium's to the right of sodium on the periodic table, so it has a slightly higher effective nuclear charge, so it is more difficult to remove that first electron. However, this trend flips for ionization energy 2. Sodium will have a much higher ionization energy 2 than magnesium, because the second ionization of magnesium removes a valence electron, bringing it to Mg2+, which is what we know magnesium prefers. whereas the second ionization energy of sodium removes a core electron, which is not preferred. Therefore, it will have a very, very high energy to do so. All right, electron affinity is another trend that we're going to talk about. This is often confused with ionization energy. They're both dealing with electrons, and that's why I think it's so challenging. Electron affinity is dealing with the energy released. If we're talking about energy released, that would be a negative electron affinity for your delta H. Sometimes these will all be written as positive, just for graphing reasons, essentially. When you have an atom in the gas phase accepting an electron. So this was very similar, but before you had the electron as a product forming a cation with your original atom. Here you have an electron as a reactant forming an anion as your product. So electron affinity is often more important when we're talking about nonmetals, where ionization energy is maybe more important when talking about metals, since the metals tend to be cations and nonmetals tend to be anionic. So this is the definition for electron affinity. There is not nearly as good of a trend associated with electron affinity, though the same rationale can be used as we used for ionization energy. There is maybe a left to right trend that you can see, again, based on you can maybe see a left to right trend there based on the effective nuclear charge. The vertical trend isn't really there, so we're not really going to talk about that. And looking closely at this, there doesn't seem to be much of a trend. This shows it a little bit more clearly, I think. And here you can see going from something like hydrogen through fluorine, there's an increase. Sodium through chlorine, there's another increase. So there is some trend here, especially from left to right. So electron affinity is increasing from left to right across a period due to the increase in effective nuclear charge. So it becomes progressively easier to add a negatively charged electron as the positive charge of the element's nucleus increases. So you're increasing Z effective. That'll make it easier to add that electron. Okay. The last one we're going to talk about is metallic character. We already know something about metals. They tend to be shiny, malleable, good conductors of heat and electricity. They have low ionization energies. That is part of the reason why they commonly form cations, where nonmetals, we know, have higher ionization energies because they have higher Z effectives. Nonmetals vary in color. They tend to not be shiny in appearance. That's associated with metals. They're brittle. They're not malleable. Poor conductors of heat and electricity. And they have high electron affinities. So they commonly form anions. And we kind of already know all of this. But means we can also make a metallic character styled trend on the periodic table. Metallic character increases from the top to bottom in a group and decreases from left to right within a period. So this actually goes similarly to the atomic radius trend. As you're going down into the left, you are increasing metallic character, which makes some sense. You have this barrier between nonmetals and metals called metalloids, or semimetals, which, like we've talked about in the past, these are the semiconductors and that sort of thing. Those are somewhere in between metals and nonmetals, and that's the barrier between the upper right-hand corner, which are nonmetals, and the bottom left, which are all metals. So that is the distinguishing factor for this metallic character. Metallic character will increase as you go down and to the left.